This is our lesson for section 7.8 using exponential and logarithmic functions. In our problems today, we are going to be solving application models or application problems that involve exponential growth and decay models, which we will solve using logarithmic functions. So the first thing I want to point out is we are going to be using scientific models. You actually need to learn the base scientific models, which can be found right here for exponential growth and for exponential decay. It's really the same base model. This equation you'll see in the book is used in banking more frequently, but it's the same basic premise. Y is replaced by A, the lowercase a is replaced by P, K is R, and they basically are meaning the same thing. In our model, A is the initial amount, Y is the amount you have after some period of time has elapsed. So T is the time, and then K is the constant rate of continuous growth. It is usually a percentage in a problem, but it is always expressed as a decimal in the formula, sometimes a scientifically notated decimal, as we'll see in some of our examples. The only difference between the growth model and the decay model is our equation is y equals a times e to the negative kt, and that's because our model is showing the amount of whatever it is that's decaying is decreasing over a period of time. But A is still the initial amount you have, Y the amount you have after a period of time has elapsed. K is the continuous rate of decay, sometimes expressed as a percentage, but in the formula used as a decimal. Its decimal equivalent, and if it's a decay model, you need the negative KT. Where do we use these models? Well, the growth model's used in any situation where something is growing over a period of time. For instance, population might be growing. As far as a decay model, population sometimes decays, but it's probably more often used in growth. A place where you might see a decay model is like radioactive decay with isotopes used in the field of medicine. There's all kinds of scientific uses with exponential decay. We do have some alternative forms here. We're not going to really use them that much, although you may encounter them from time to time. They are alternative forms. They don't give the exact same answer, but something practically equivalent. The exponential growth model is y equals a times the quantity 1 plus r raised to the t, and the decay model is y equals a times the quantity 1 minus r raised to the t. In the model, a is still the initial amount, and y is the amount you have after a certain period of time has elapsed. R is either the rate of growth or the rate of decay, again, sometimes given as a percentage, but in the formula expressed as a decimal. And in the growth model, it's 1 plus R, and then in the decay model, it's 1 minus R. Where do you see these formulas used? Maybe more with assets. Assets are things that you own that have value that either increases over time or decreases over time. For instance, a house, typically, if you live in it long enough, increases in value over time. Collectibles, if you collect trading cards, those types of things increase in value over time, typically, or artwork. Exponential decay is when we have assets that depreciate over time. And probably the best example is a car. As soon as you drive it off the lot, it decreases in value. So those are just situations we might use these two models. Could we do the same thing with the scientific model? Absolutely. And the scientific model is the one that I require you to use when we take our tests next Tuesday. So you need to learn y equals a times e to the kt and y equals a times e to the negative kt. Whether or not you learn the banking form is up to you. I would probably just use the generic growth model. All right, so let's look at some examples where we use these. The worksheet that the substitute gave you, you can fill in on this, and the problems we skip are the ones that you need to finish for your homework in addition to the problems in the book. And if you look, the first equation, it says in 2000, the world population was estimated to be 6.124 billion people. In 2005, it was 6.515 billion. First observation I want to make is that the population is expressed in billions. They use the word so you don't have to write all the zeros. So 6.515 billion really means 6,515,000,000, and there are technically 6 zeros that would follow. Do we want to write all those zeros and that whole long number out? Probably not. That's why when you plug in for a and y, as long as a and y are expressed in the same quantity in billions, we don't have to write all those zeros, and we can express it as 6.515 billion and 6.124 billion. Notice in the problem in 2000, the population was 6.124 billion, but in 2005, it was greater at 6.515 billion. As a result, this is a growth model. And you can see they've given you a growth formula here. And you can see that what they plugged in for A is the 6.124. Of course, you have to know in your mind that's billion. And for Y, that's the amount you have after 6 years or 5 years have elapsed, because 2000 to 2005. So notice for T, they plugged in 5. As far as E, that's our base, and K is the value that is showing the rate of growth. So we're trying to find that. So to solve our equation, if you look, from the first line where we plugged in, we divide both sides by 6.124 to get this second line. Then we take the natural log of both sides. Notice I didn't approximate anything yet. The beauty of taking the natural log on the right side is because the base is e, that cancels out and you're just left with the exponent, or 5k, on the right side. And then we divide both sides by 5. So we get 0.01238. That is really meaning when you look at that decimal and move the decimal 2 places to the right, that's about 1.2%, give or take. So that's the value of k that we're going to use to do part B. Because part B says, when will the world's population reach 7.5 billion? And in this problem, the initial population from 2000 is still 6.124. We want to know when it's going to reach 7.5 billion. It's still in the billions. We're trying to find T, how long it takes, but now we're going to use that answer we got for K in part A in our formula. And you can see that right there, the 0.01238 times T. How do we solve? Well, we divide both sides by 6.124. We've isolated the exponential terms, so now we can take the natural log. The beauty on the right side is that cancels and just gives you the exponent, or 0.01238t, and then we divide both sides by the 0.01238, and we get t is about 16.3722, so roughly 16 years. It would round down. So we can say the world's population will reach 7.5 billion in the year 2016. All right. So now let's try ourselves. We're going to do a few of the problems on the worksheet here, and then the rest you will finish for homework, plus the additional book problems that are listed in Canvas. So number 1, carbon dating. This is a formula that is used in archaeology. It's a known formula. It's given to you right here. Y equals A times E to the negative 0.00012t, and it tells you that A is the initial amount of carbon-14, T is the number of years ago the animal lived, and Y is the remaining amount after T years. It's important to note that Y is the remaining amount of carbon-14 after T years have elapsed. So in part A, it says, how old is a fossil that has lost 95% of its carbon-14? So the first thing I want to point out, if it has lost 95%, the question is how much remains, because remember, we want to know Y is how much remains. So in part A, which I'm going to come down here, here's my formula. Y equals A times E to the negative 0.00012t. I need to understand, I don't actually know how much carbon-14 I actually had to start with, but I'm going to call that 100% or 1. And in my formula, I'm just going to leave A, the initial amount, as A. And what I'm going to plug in for Y, if I lost 95%, that means 5% remains, and I'm going to plug in for Y with 0.05 times A, because that's the percentage of what I had, and I leave the A, and so this becomes my formula. Of course, what happens is the A's cancel out, and I really have 0.05 equals E to the negative 0.00012t. At that point, I can take the natural log of both sides. So the natural log of 0.05 equals the natural log of E raised to the negative 0.00012t. And the beauty is, since the base of the natural log is E, on the right side, all of that cancels out. And so what we really have is the natural log of 0.05 equals negative 0.00012t. Of course, to solve for t, we're just going to divide. T is going to be equal to the natural log of 0.05, all divided by negative 0.00012. And that gives us about 427. Try it in your calculator to make sure you can enter it correctly, but that means this fossil is about 427 years old. Now, how about part B? So that was part A. Part B is a little different. Oops, you know what? I just gave you the answer for that's the answer for part B. So erase that here. The answer for part A, I was looking at my notes wrong, is 24,964 years old. Now, sometimes you're going to notice in our book may round that answer and say about 25,000 years old, and that's fine. You could round to the nearest thousandth, or you could just leave it 24,964. All right, part B. Part B says, how old is a skeleton that has 95% of its carbon-14 remaining? Since Y is the amount remaining, when we plug into our generic model, which again, I can write it right here, Y equals A times E to the negative 0.00012t. What's different here is the 95% is what's remaining, and so it's 95% of whatever you started with. Since we were never given an amount, we generically leave A as A, and for Y, we put 0.95A equals A times E to the negative 0.00012t. At that point, we can cross the A's out and take the natural log of both sides. So the natural log of 0.95 would equal the natural log of E to the negative 0.00012t. Now, if you understand that because the base of the natural log is E, that's all going to cancel, you might get to the point that you actually bypass that line and you say 0.95 equals, or not 0.95, sorry, the natural log of 0.95. Let me get that. The natural log of 0.95 equals negative 0.00012t. And that's fine. It depends on your comfort level. So to solve for t, of course, we will divide. And I have the natural log of 0.95 divided by negative 0.00012. And like I said, that is about 427 years old. All right, did you understand that? Hopefully, yes. If not, I'll address your questions on Friday. Let's move down. We're going to look at two problems here, at least the setup for two problems on the back side. So that's number 1. We'll get it set up. And number 5. So in number 1, it says, in an overfished area, the catch of a certain fish is decreasing exponentially. So first clue, decreasing, that would indicate an exponential decay model, which basically is A times E to the negative KT. Notice they don't tell you K is negative because they give that as 0.084, but the fact that it's decreasing means you need to have that minus. And it says, use that value of K to determine how long it will take for the catch to reach half of its current amount. We actually don't know its current amount, but we want half of what it was. So in our generic model, we're going to leave AA, but we're going to make Y half of that, or 0.5A. So 0.5A is going to equal A times E to the negative, and then I'm going to plug in with the K value, 0.084, t. And yes, the a's will cancel, and I'll have that 0.5 equals e to the negative 0.084 t. That looks a little messy there. Let me get that. 0.84 t. And of course, at this point, I'm not going to show you all the work, but you should understand that you're going to take the natural log of both sides, like we did in the previous two examples, and then you'll have the natural log of 0.5, and you'll have to end up dividing by negative 0.084, and that should give you your answer, and I'll tell you what that is. You need to obviously go through the work and make sure you get the right answer, but it should be about 8.3 years. I just don't have enough space writing with my Apple Pencil. All right, that's number 1. Notice for y, we put 0.5a because we wanted to know how long it would take for the fish population to reach half of it originally was. All right, the other problem, number 5. If we take a look at 5, it says the element plutonium-239 is highly radioactive. Nuclear reactors can produce and also use this element. The heat that plutonium-239 emits has helped power equipment on the moon. If the half-life of plutonium-239 is 24,360 years, what is the value of K for the element? Now, we are dealing with a decay model because half-life really means the amount of time it takes to get half of what you currently have. It's really essentially what is happening in number 1. How long does it take for the current population to reach half its current amount? Well, that's what half-life means. So that is definitely a decay model. Y equals A times E to the negative KT. And we don't know how much plutonium-239. So again, we leave A as an unknown. And for Y, we're going to put in 0.5 A equals A times E to the negative K, which we want to find K. And then for T, we're going to put 24,360, which is a pretty big number. The A's drop out. We'll take the natural log of both sides. We'll have to divide by negative 24,360. And this is where we get K. Now, K may come up on your calculator as a scientifically notated number. On my calculator, it says K is 2.845, blah, 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 blah. And at the end, it says E negative 5. What you need to understand is that's like times 10 to the negative 5th. That's what E negative 5 means at the end of the line. So if you move your decimal point 5 places to the left, you would move it 1 place around the 2, and then you would have to add a 0 in front. So another way of writing this would be point, and then you'd have 1, 2, 3, 4 zeros, the 2, and I'd probably go 8, 4, 5. I like to at least have enough digits for the greatest accuracy. I don't want to have to write all 9 digits out, but probably at least 3 or 4 is recommended. And that's number 5. So what do you need to do? Well, to finish the lesson, you need to finish problems 2, 3, 4, and 8 on the worksheet. I will point out in number 2, it talks about the population and, oh no, it's not 2, it's 3. It talks about the population in thousands. So when you see the 80 here for the initial population, That's really 100, or that's really 80,000. And so when it says, in how many years will the population reach 120,000? When you plug in for P, you better plug in 120, not 120,000. Otherwise, you'll get a wrong answer. And number 2, don't forget 1.5% when you plug into the model for R. You've got to use the decimal form of 1.5%. And that would be 0.015. In this problem, you're actually just solving for P because they want the population. And hopefully that helps you get a start. You may have some questions around the book problems. If you do, we'll address some of those in class on Friday. And I hope you find this helpful. You may help each other. All right, have a good day.